Good day, everyone. This is a lecture on conventional site remediation methods. The objective of this lecture is for the student to be able to select site remediation methods with due consideration of the access, economics, remediation rate, and other factors. Note that the choice of cleanup technology for a contaminated site depends on various site conditions like the type of pollutants, concentration distribution, soil and geology, hydrogeology, and other factors such as the time frame, like the urgency of the project to be completed, the efficiency of the method when we are talking about a large scale contamination versus a spot contamination, the intended land use of the site, like for example, residential area versus an open field, the receptors, like building occupants who are always on site versus occasional visitors for a park, also risk assessment, economics, and physical constraints, like how is the site in terms of accessibility, and so on. Physical methods involve those physical movement of your contaminated phases like excavation, soil vapor extraction, groundwater pump and treat, dual phase extraction, multi-phase extraction, high vacuum pump, air sparging, thermal, and granular activated carbon sorption. Excavation basically is just to remove the contaminant sources like your an impacted soil, then either you transport it off-site to dispose or you treat it to remove the contaminants. The advantage of excavation is that it's a fast solution, especially when you have a short time frame and you have to move on with your project. And it is a good alternative when you have no other choices, and especially if your site is a fine-grained material like silt and clay, where other methods such as soil vapor extraction is not so effective. The limitation of this method is that it's, of course, it's expensive per volume. It's also disruptive in a sense that you may have to halt the business activities in the area, and it's also just limited to areas with a proper access, like open fields. This is quite difficult to do if your site is an existing structure. You can't really dig beneath a building. Also, the method does not dig very deep. Typically, if you're talking about manual excavation using human labor, it doesn't go beyond 1 meter. And if you're using a backhoe, it doesn't go beyond 5 or 4 meters. There are other methods like deep or large diameter borings, but first they can get expensive quite fast. Another limitation of the excavation method is that it doesn't destroy the contaminants. Here is an example of a site excavation. On your left is an open pit soil removal, and on your right is a deep soil digging with shoring and boarding to prevent soil cave-in. So you can see here the yellow fence on the lower right of the photo, that's your shoring and boarding. So you are sort of putting in some temporary walls to prevent the soil from collapsing and crashing in back to excavation. This is a large diameter drilling rig for removing deep into your impacted soil. The next physical method is the NAPL removal. This is basically just bailing or pumping out. Bailing means you're just scooping out the water. The non-aqueous phase liquids, alright, which are typically in form of a free product, meaning it's a separate phase from water. Note that most NAPLs or your light NAPLs have low density and flow freely and can easily be elevated into the surface by just pumping in water. Alright, so this is just doing it by the displacement method. However, if you are dealing with dense non-aqueous phase liquids or DNAPLs, they just sink to the bottom of the aquifers and they're impossible to remove by pumping in water. Alright. The advantages of NAPL removal is that it's effective for small quantities of free products. And since you're just bailing out, you're pumping out water, it involves minimal disruption of the site activities. Limitations of the method is it's quite slow. Alright, you're just manually or automatically trying to pump out the contaminant, and it's almost impossible to operate continuously with the NAPL removal because this is quite labor intensive. Also, it's ineffective for a low permeability groundwater formations or for low permeability aquifers because when you have low permeability formations, you tend to have small soil grains, and small soil grains have a large surface area for sorption, meaning you can expect a lot of your contaminants to stick in the soil grains. So it's quite difficult to completely remove NAPLs which are sticking on the soil grains, and you may want to use other methods which will be discussed later. This is an example of a NAPL removal by baling. Okay, so basically they're just trying to scoop out the El NAPL from a well. Another physical method is the groundwater pump and treat. This is different from NAPL removal in a sense that we in here we are actually taking out the groundwater, treating it, and sometimes you just put it back or we return the treated water into the aquifer. So it's a three-step process of taking it, treating it, and putting it back. Alright? And the coverage area of a groundwater pump and treat method is dictated by the capture zone of your treatment well. So this capture zone is approximated by your cone of depression. Alright? And it might be necessary to use multiple wells to ensure that the capture zones of your wells are actually covering your target contaminants. Alright, although there's this phenomenon with pump and treat that the contaminant concentrations can only reduce to a certain limit. Alright, you will eventually just reach asymptotic levels of contaminant concentrations, meaning you can never completely remove the contaminants using groundwater pump and treat. Okay, this is caused by the sorption of your contaminants in the soil. Okay, or a phenomenon called tailing. And also, after pump and treat, after a certain period of pumping and treating and removing the contaminants in the groundwater, it is possible for your contaminants that were initially sorbed in the soil to re-equilibrate with the clean groundwater. So it means that the contaminants that were attached to the soil particles can be released again into the groundwater, which will result in recontamination of your groundwater. We call this phenomenon the rebound. Here's just a figure of your groundwater pump and treat method. Alright, so you have a well that is pumping out your water, and depending on the pumping rate, you can create a zone of influence called the cone of depression. And more or less, that area under the cone of depression will be pumped pumped in into the well and is available for treatment. All right. Now, note that there are various ways to pump, or rather to treat a groundwater once you have taken in you have pumped it into to the surface. For example, you can use for organic contaminants in your groundwater, you can use air stripping, granulated granular activated carbon sorption, chemical or ultraviolet UV oxidation, and aerobic biological reactors. For inorganic constituents, you can use chemical precipitation, ion exchange, adsorption, reverse osmosis, and electrochemical methods. Now, once you are done treating your water, you can either discharge it to your sewer system or put it back to the aquifer to conserve water. Now, the advantages of this method is that it conserves water, and also the ex-situ or off-site treatment methods allow you to more efficiently treat the water, meaning you're just directly dealing with the contaminated water once you take it to the surface. So you just need limited amount of chemicals or limited amount of processes to treat the contaminated water compared to other in situ methods, which I will be discussing later. Alright? And this method is also effective when you are dealing with a contamination in a concentrated spot. Now, the limitations of this method is, of course, it's impossible to get zero concentration or very low concentration levels in groundwater pump and treat. And you are have to deal with the tailing and the rebound effect, which guarantees that the contaminants will be there will be always be residual contaminants after you do your pump and treat method. And in other cases, when you are actually dealing with a large scale contamination, especially when your concern is water supply treatment, it actually might be more economical to just extract the contaminated water to your water treatment facility and directly treat it from there. Another method or another physical method is the soil vapor extraction. This is used in the vadose zone or your non-saturated soil zone, and it uses or relies on vacuum pressure to extract the volatile compounds from your porous soil. So It's similar to your to a vacuum cleaner that you're just sucking in the volatiles. All right, and its ranges of influence is all right. It can be estimated from pilot testing, meaning you do one soil vapor extraction on site, and then you monitor the areas where the contaminants were actually extracted. All right, and also note that contaminants that are sorbed in the soil, all right, also undergo the rebound phenomenon. Okay, so after initial extraction of the vapor, pausing the extraction process allows the contaminants to re-equilibrate with the soil and evaporate again. So one advantage of the soil vapor extraction method is you can do a pulsing or an alternating mode. So you suck out the vapors, you rest for a while, and then you suck out the vapors again until you completely remove the vapor phases. And this method can be coupled with other vapor treatment methods such as granular activated carbon, catalytic oxidation, and thermal oxidation. This is a schematic of a vapor extraction system. As you can see in this block diagram, you have essentially have wells which are connected to a vacuum pump, and this vacuum pump, all right, draws in all the vapors into your perforated pipes. And once they are drawn in into the surface, they can be treated above ground. Some typically they're just ignited or combusted, or sometimes use the other vapor treatment methods mentioned earlier. Now, the advantage of soil vapor extraction is it's effective in coarse soil like sand, gravels, and this is mostly a machine-based method, so it can be done continuously. And the added benefit of soil vapor extraction is you are increasing the airflow in the soil, meaning you get to introduce a lot of oxygen. And if aerobic biodegradation processes are beneficial to your site, for example, if you have organic compounds like petroleum products like benzene, the introduction of additional oxygen can accelerate the aerobic the biodegradation of your organic compounds. The limitations of this method is that it's only limited to your vadose zone and to your volatile contaminants. So you're just dealing here with your vapors. And it's not effective in fine soils, where of course it's fine soils are have small air permeability, just the way water has a low permeability in water. Oh, sorry, water has low permeability in fine soils. Another method is it's not really a method, but this is more of a an add-on to the physical treatment methods. This is the thermal enhancement by electrical and natural gas heating. What we're doing here is we are introducing heat to speed up the volatilization process. Okay, so meaning we heat up the contaminants so that they evaporate. And this is typically coupled with your soil vapor extraction method, although it's also useful for other methods that are done in the groundwater. So this is quite a flexible method. It can be done in the vadose zone, and it can also be done in the saturated or the groundwater zone. Alright, though note that in order to heat up, you either use natural gas or electricity. And of course, electricity is expensive. The advantages of this method is if money is not, okay, if you have no problems with spending a lot, okay, you have a high budget for a project, thermal enhancement can produce fast results. And you can also note that heat flow has a limited impact area. Okay, heat flow is always tends to not really spread out, so it has a small impact area. The limitation of this method is of course, it's expensive. Here is a here are two diagrams. First is the schematic of a gas-based heating system. All right. So you have here pipes which are using gas to introduce heat to your soil. And the other figure is a heat monitoring map to see how effective is the method and where is the heat distribution occurring in your treated site. These are photos of the equipment used in thermal enhancement. First is an electrical pole, alright, and this is a close-up, and the photo is just a zoom out or a perspective view of an electrical pole used for heating the soil. Another physical method is the dual phase or multi-phase extraction and air sparging. Alright, so this is not actually a separate method, but this is a method which combines different physical methods in order to attain a comprehensive cleanup. So what happens here is we are extracting dissolved contaminants in vapors by air injection to induce volatilization. So that's what we call air sparging. Okay, when you are injecting air into the ground that to induce volatilization, that is air sparging. Okay, so when you are doing this in the capillary fringe, okay, so this is a dual phase. It's a dual phase extraction because you are removing the dissolved contaminants and the vapors. All right. Now, if you are extracting the free products of your NAPLs and you're also removing the dissolved contaminants and also removing the vapors, which is done by screening your extraction well across the vadose zone and the capillary fringe and the groundwater. So you are essentially extracting three phases here, and it can be called a multi-phase extraction. And of course, as above, this is also accelerated by air sparging. Okay, so this is a complex method where you are pumping in air to promote uh, volatilization, and you are also using groundwater pumps to extract liquid contaminants, and you're also using vacuum well pumps to extract your vapors. All right, so it's a combined system, and the advantages of it is, of course, you get to remove all the contaminants in all phases. And it's effective for contaminants in the capillary zone, which is common for an NAPL. The limitations of this method is, of course, it involves complex engineering. You're dealing with three different technologies, and if you don't really understand what is happening, you might be just spending a lot on a design, but that is not may not be really well suited for your problem. All right, this is a diagram of your a multi-phase extraction system. All right, as you can see in the block diagram, you have a your groundwater table, and you have your dissolved contaminants shaded by diagonal lines. So that's your contaminants in the groundwater. And you also have your adsorbed phase in the vadose zone, or the materials that are shaded lightly in gray. And you also have a sort of a lightly shaded color, which is the vapor phase. Okay. Okay, so you can see here that the extraction well is screened across the vadose in the vadose zone and in the groundwater. And you also have some black stuff here. I think this is a free product El Napol. All right, so you have vapor, free product, sorbed, and your dissolved phases. So you are trying to extract here these four phases. All right. Another method is the barrier installation method. This is actually not a mitigation method, but just a protection method, because you're not really removing the contaminants in any meaningful way. What you're actually doing here is you're just putting up a barrier between the contaminated soil or groundwater and the floor of the building. Alright, so this is to prevent vapors from entering the building and reaching your receptors, which in this case are your building occupants. Normally, your vapor barrier is a sandwich of low permeability materials, and in the middle is a porous materials which is meant to catch any escaping vapors. All right. The advantage of this method is, of course, it's inexpensive, especially when you're just constructing a new building. The limitation is, of course, it's not a treatment method, and the contaminants can still migrate to somewhere, and it's not practical when you are dealing with extensive contaminations. And it's also challenging to implement for an existing structure. Now let's talk about the chemical methods. Now there are some guidelines in the use of chemical methods. Alright, so first is the common chemicals used in both in situ and ex situ chemical methods. You have your hydrogen peroxide, your ozone, your potassium permanganate, your sodium permanganate, and other reducing agents such as ferrous chloride and zero valent iron. Alright, now the application of chemical methods is, of course, when you are dealing with chemical reactions, you need an aqueous solution. So, chemical methods are mostly limited to the aquifer or to the saturated zone. Alright, next is the goal of a chemical method. Alright, an optimal chemical treatment method will use a minimum or limited quantity of chemicals, and that the chemicals used should not actually exacerbate or worsen the pollution problems. And these goals are achieved by a staged process. So, meaning we do this in different scales. We start with a bench scale demonstration in a laboratory where we try to see if the chemicals would actually react with the contaminants. And then we conduct a pilot test of the chemicals in field conditions. So meaning we do a field testing in a small scale, and if it's successful, we conduct a full-scale application and we monitor the results. Now, there are two main types of chemical methods. One is the in situ chemical treatment, and the other is the ex situ chemical treatment. Right? For the in situ chemical treatment, what we do is we directly inject the chemicals and hope that they react with the pollutants as much as possible. And the typical applicator or equipment used to do in situ chemical treatment is the direct push method, which is basically a hollow steel rod with an injector. Okay, so we push a rod into the ground, and it has an injector which introduces the chemicals into the subsurface. All right, so the reach of the chemicals depend on the injection pressure, and of course, the more porous the aquifer is, the better. And this is done by doing a grid of injection points. And there should be a caution in applying too much pressure, because overpressuring can cause the chemicals to just spurt back to the surface. Alright, the advantage of this method is it's it doesn't use a lot of water, because you're simply directly injecting the chemicals into the subsurface, and it can be also relatively cheaper because the equipment that you use is just the direct push equipment. Okay, now the issue or the limitation here is it's quite difficult to monitor the results of an in situ chemical treatment. Okay, first is because you have to put monitoring wells, and second is there's actually a lot of natural processes that will attenuate your contaminants. So you have your dispersion, you have your diffusion or the spreading of your contaminants, which causes them to dilute. You also have your sorption processes, wherein your contaminants just stick to the soil grains. Alright, you also have your decay processes, which involve the chemical and biochemical reactions within the soil. So it might be difficult to quantify or measure if the chemicals that you introduced in the site were actually the ones that were working on the contaminant, as opposed to natural attenuation processes. Here is a figure of the direct push rod method. Alright, so it looks like an SPT rod. but it has hollow points which allow injection of your chemicals. Now, the second major type of chemical treatment is your ex-situ chemical treatment. So this is essentially just a pump and treat method plus chemical treatment methods. All right. So the advantage of this method is, of course, you get to control the chemical reactions because all the treatments occur in the surface in your treatment plants, and it can potentially save water if you can re-inject the water back. All right. Now the limitations of this method is, of course, you need to install a treatment facility which will require space and will have added costs. And of course, it's also expensive to pump out water and re-inject it back again. Now we move on to the biological methods. In biological methods, we just let the living things, aka your bacteria, to consume or hold your pollutant. So actually, it's not just bacteria. We also use plants. All right, so we use bacteria or bioremediation or plants, which is also called phytotechnology, to handle your contaminants. All right, and part of these treatment methods is you have to feed your agents, right? In the case of bacteria, might have to provide sugars. In plants, you may have to provide fertilizers. Now, the function of bioremediation is when you're using bacteria involves redox reactions where the or reduction oxidation reactions where the contaminants end up as harmless products like carbon dioxide or ethane. And of course, as you are using bacteria, when if you're gonna use bacteria, you have to take care of your bacteria so that you can ensure their propagation. And bacteria have three broad categories in terms of their needs. One is your carbon source that can feed them. You also need an electron donor, all right, for their redox reactions, and also a terminal electron acceptor. Okay, all right. So note that each species of bacteria has enzymes to catalyze only certain redox pairs. So you have to be highly familiar with the redox reactions that are necessary to catalyze your contaminants. Right? So you have to understand what type of redox reaction do you need to occur. Okay? Once you identify that, you have to look for the specific species of bacteria that can catalyze that kind of redox reaction. So you have to tailor fit the selection process of your bacteria for the type of contamination that is present in your site. All right. Now, when you need an oxidative bioremediation process, all right, uh, these are the typical contaminants that can be treated using your oxidative bioremediation. So you have your petroleum products like gasoline, fuel, diesel, benzene, toluene, ethyl benzene, and xylenes or your BTEX. Also your gasoline additives like your MTBE or your octane booster. Also your solvents such as acetone and also polycyclic aromatic hydrocarbons or PAS, which are commonly used in soaps and other detergents. You also have your pesticides and herbicides such as pentachlorophenol or PCP. You also have your vinyl chloride, dichloroethene or DCE, which are typically your products from biodegradation of chlorinated solvent compounds. Now, the other side of the redox reaction is the reductive processes, and this is mostly applicable to contaminants in their oxidative states. That includes your chlorinated solvent compounds, including PCE, TZE, TCA, also your perchlorate, and also your demolition explosive or your RDX, okay, where your TNT components are reduced into amino substituents, which essentially turn into soil fertilizers. You also have your pesticides and herbicides that are susceptible to anaerobic reduction, so meaning no reduc degradation in non-oxidizing conditions, such as pesticides, such as toxaphene and dieldrine. You also have your semi-volatile organic compounds such as creosote and PCP. And reductive bioremediation is also effective for hexavalent chromium, which can turn it into to the less harmful trivalent chromium. And there are also various metals which can be precipitated into metal sulfides using uh, reduction. All right. The advantages of bioremediation is it can handle a wide variety of contaminants. Now, the limitation of bioremediation method is the bacteria themselves, okay, can grow exponentially even after the treatment. So you can get an uncontrolled growth of your microbes. The other type of biological method is your phytotechnology, wherein you use plants to remediate or contain contaminants. So take note of the difference between remediation and containment. Alright, remediation is about removal or conversion of your contaminants into their harmless forms, while containment is about immobilizing or storing your contaminants and so that they are isolated from your receptors. Okay? Now, the basic mechanisms involved in phytotechnology include sequestration or meaning extraction of the contaminants, degradation or the breakdown, volatilization or evaporation of your contaminants, and hydraulic containment, or meaning your plants can create a permeability barrier to contain your contaminants. All right, so sorry, sequestration or sorry, it means storage. So sequestration is about taking out the contaminant and storing it in the plant. And this can occur in your root zone or in your transpiration stream, which includes your stems and your leaves. All right. So it's important to distinguish the two areas, because if your strategy in your remediation is to harvest the plants that have the contaminants, okay, you have to make sure that the plants are sequestering the contaminants into their transpiration stream. All right. Now, if you are using a plant that is storing the contaminants in the root zone, it won't be practical to harvest those plants because as you harvest the plants, you'll be essentially killing them by removing their root zone. Okay, so at least when the plants are storing it in their transpiration stream, it's convenient to just cut off the stems and leaves of plants and let it grow again. All right. Now, let's talk about the degradation process in plants. Now, the degradation can occur in either in the rhizosphere or the root zone or the plants and stems. Okay, once the plants have sequestered the contaminants in the leaves and stems. Now, the rhizodegradation or degradation in the root zone is actually a is about the plants creating an environment that is more conducive for breakdown. So what they do here is they store the contaminants in the root zone, and then the plants release chemicals that can help the bacteria in the soil to break down the contaminants. So the plants might release sugars, alcohols, or carbohydrates, and these will be consumed by the bacteria, and they get to metabolize faster, which will in turn help in the breakdown of your contaminants. Now, in the phytodegradation or degradation in the stems and the leaves, this involves enzymes that are used by the plant to break down your contaminants. All right, so basically enzymes and oxidants and reductants. So these are produced during the photosynthesis of your plants, and these help break down your contaminants inside your plant. So this is quite different in rhizodegradation, where the degradation is actually still occurring in the soil, okay? But it's just accelerated by the plants who are essentially feeding the bacteria around so that the bacteria can break down the contaminants. Now, the other process is the volatilization of contaminants, and this occurs in the leaf stomata or in the plant stems. All right. Now, note the added benefit of having the plants volatilize their contaminants. Typically, when your plants volatilize your contaminants, the plants also release, uh, also tend to help form hydroxyl radicals. Okay, so the hydroxyl radicals produced near the plants react with the volatilized contaminants as they are released in the air. Okay? Now, let's talk about the phytoremediation or the use of plants to remove or delete your contaminants. Alright, so there are certain types of plants that are called ground covers. Okay, so these are your small plants that cover the ground, and they have been used to soils that are impacted by recalcitrant compounds, meaning compounds that do not easily break down, such as PAS and PCBs, and other POPs or persistent organic pollutants. So these are your insoluble, immobile, and non-bioreactive pollutants. So they can be remediated by your ground cover types of plants. Also, ground covers have been used to extract certain organic contaminants such as metal salts and radionuclides. Another form is the tree stands, which are trees that can be used to conduct phytoremediation. So they have been used in soil or groundwater impacted with soluble contaminants like your BTEX, MTBE, aliphatics, gasoline range organics, diesels, and total petroleum hydrocarbons and chlorinated hydrocarbons. Okay, you know that chlorinated hydrocarbons are mostly your plastics. Alright, another function of your phytotechnology is the phytostabilization. This is more of a physical function of the plants. So what we do in phytostabilization is just to prevent the soil from migrating or from eroding, or to prevent the contaminant from migrating. So this also involves another function called phytohydraulics, wherein the root system of your plants act as an erosion control agent. Okay, so the root systems bind together your soils so that you can reduce or prevent soil erosion. Alright, so phytostabilization also relies on another function called phytosequestration, wherein the contaminants are stored in the plants or in the zones near the plants. So this prevents contaminant migration. Okay, and another subsidiary function used in phytostabilization is the use of trees as hydraulic barriers. Okay, so the root systems of the trees can provide barriers from plumes from going any further within the groundwater. Okay, so if your tree roots are deep enough to and dense enough to create a hydraulic barrier on a groundwater plume, okay, can be used as a plume control. Okay, so now the use of plants as hydraulic barrier involves deep-rooted and high-transpiring trees, okay, which can tap into the groundwater. So it should be deep enough to tap into the groundwater, and it also should have a high transpiration, so it can quickly draw in the water and alter the path of your contaminant. Another function in phytotechnology is the use of constructed wetlands. And these are man-made wetlands that are used for removing various types of contaminants in your water. And this one relies on microbes in the soil or sediment. And another keyword in constructed wetlands is it is self-sustaining, and it utilizes different phytotechnology functions such as phytosequestration or storage, rhizodegradation or breakdown of contaminants in the root zone, phytoextraction or storage of contaminants in the leaf and stems so that they can be harvested, and then phytodegradation or the breakdown of contaminants in the leaves and stems, phytovolatilization or the evaporation of contaminants through the leaves, and phytohydraulics or the stabilization of soils using roots of plants. Alright. The advantages of phytotechnology in general is it's the most comprehensive among in situ technologies because it can be used in both organic and inorganic contaminants. So it can cover a lot of types of contaminants, and it can be applied on a wide range of environmental conditions. You can use it in the redox zone, in the capillary zone, in the groundwater. All right, and it also allows simultaneous treatment of those zones. And another important benefit of phytotechnology is the green and sustainable technology. I mean, it's easier to sell to your stakeholders. It's also easy with the media, all right? And it's probably uh, potentially profitable if you want it as a business. 'Cause, you won't have trouble marketing the technology. And another advantage is the low capital costs because you're just using plants and trees to do the remediation process or the containment process, as well as the aesthetic nature of planted sites. I mean, of course, everyone will prefer trees over pumping wells. Okay, so that's a plus point for phytotechnology. Now, the limitations of phytotechnology is you have a limited depth, right? Typically, the maximum depth that was ever reached by phytotechnology is 40 feet or 15 meters. Okay, although the practical limit or the general rule of thumb is that trees will not go beyond 5 feet into the saturated zone. So you can practically just remediate the upper 1.5 meters of your groundwater when you're using phytotechnology. All right. So other limitations. Sorry. Yeah, yeah. It's mostly about the penetration depth. Okay. That's the main limit of your phytotechnology. So that ends the lecture on uh, i- contaminated site remediation methods. Thank you for listening. If you have questions, just mail me in the blackboard. Okay. That's all. Thank you.